Calculus students, we are going to do the homework on linear approximations. The idea we saw in class that if we have, say, a function x to the fourth, cool, where values on the function are tough to find at decimals, like 1.1 is not a value that you can easily take to the fourth power without a calculator, okay? But we can create equations of tangent lines easily. So what we can do is create an equation of a tangent line at 1. It's a very easy tangent line because we got the point 1, 1. If I plug in 1, I get 4. So that's one thing. I know the slope is going to be 4, so I get y prime of 1 is 4. And I'm going to create the equation of the tangent line y minus 1 equals 4 times x minus 1. Okay? And what have we done? Well, we zoom in at this point 1, 1, which I will do. And we keep zooming in at this point. What do we notice? The line and the curve start to just kind of blend together until you can't even notice the difference between the line and the curve. Okay? So, boom, right there. Like, I can't see the difference between the curve and the line, which means, let's say we want to approximate 1.1 to the fourth. Instead of plugging it in here, I'm going to plug in x equals 1.1 into there. And I get 1.4. That seems like so easy, but like that's powerful. And you can see what the real value is. That's 1.46. Now, are we like dead on? No, we're not dead on, but it's like, it's powerful having these lines being used. These y values are very easily found, versus 1.1 to the fourth is something that requires a lot of calculations to get 1.46 formula. Okay, so that's the idea. But let's say I asked you what is, I don't know, 2.1. Like, what's the value at 2.1? I gotta zoom out a lot. Well, like, you can see the value at 2.1. I would not use this blue line. I would instead use a new tangent line that maybe is centered around 2. We have the point 216. And we would be able to find the slope using 4x cubed, which would be 32. And boom, I would use this line to approximate points close to that line. Okay, and that's the lesson. And then we talked about how if you know the curvature, you will know whether your points on your line, which will be the values you get for your approximation, will be under or over the actual values on the curve. So you see this approximation is under the actual. We'll say this is under. Turns out it doesn't matter whether we're decreasing or increasing. It's the same. If your graph is concave up, however you draw a tangent line, your values on your line, which are your approximations, are under the values on your curve. If you are concave down, whether you are increasing or decreasing, it doesn't matter. Your values on your lines, which are your approximations, are over the values on your curve, which are your actual values. So these would be over approximations. No. Does it matter? No. It's all about curvature. Horrible example, horrible graph, but it's all about curvature. If you're curving down versus curving up, no matter how you draw something curving up and a tangent line to that something curving up, it's hard to freehand tangent lines on this thing. values are under, your approximations will be below the actuals. Here, values will be over, approximations are over. Okay. But remember, we got to use the correct point. We got to make sure we're using a point that we know and the tangent line at the point that we know that is close to the value or approximate. For example, 2.8 versus 2.1 versus 4.25. If I have f of 2.8, I would say that is close to f of 3. F of 3, which is 2. Cool. Whose slope is 5. I will use this tangent line, y minus y1 equals m times x minus x1. And I will say this line mimics whatever this curve looks like around the point 3,2. So if I want to approximate f of 2.8, which is going to be a point on my curve, I will use my line equation, and this will be a y on my line. I will plug in 2.8 into that, and I will get negative 0.2 times 5 plus 2, which is negative 1 plus 2, which is 1. This is a y value on a tangent line, and that is going to approximate the y value on the curve. Cool? If you need to do 5 times 0.2, 10 with a point. Yeah, cool. But what if I'm looking at f of 2.1? Well, 2.1 is close to the point I know, f of 2, which equals 4. Slope is negative a half. I will use this line. And I'll say this line mimics this curve around the point 2, 4. So I will try to approximate a y value on my curve, on my curving function. To do that, I will use my line and I will plug in 2.1 in for x to get a half times a tenth plus 4. You could think of this as 0.5 times 0.1, which is negative 0.05. You could also, I'll show you just 2 different ways to do this. You could do negative 0.5 times 0.1, which is negative 0.05. You could also turn 1/10 into 1/10. Negative a half times 1/10, you get negative 1/20. Then if you're adding 4, it's probably easy to see this is 3.95. You would do this. If you're adding 4 as a common denominator, you'd add 80/20, and you get 79/20. Okay? This is a y on a line that is approximating a y on a curve. And 4.25 is close to a point that we know, f of 4, which equals 3, whose slope at 4 is 2. So I'm going to use y minus 3 equals to x minus 4. I will approximate a point on my curve by finding a point on my line. At 2 times a quarter plus 3, that's probably easier than 2 times 0.25. I get 3 plus a half, which is 3.5. So my y value on my curve is approximately equal to 3.5, which is a y value on my line. That's it. That's the lesson. This is probably going to be further plus. If f double prime are your approximations over under, let's say for all 3 of these, we're talking about a function, a curve that's curving upward. What would we say these approximations were? Well, like no matter how you draw it, and you need to draw it, draw something that's curving upward, draw a tangent line, and you'd be like, oh, all of the points on my lines, no matter where they're located, are below the points on my curve. So my approximations are under the actuals, or you could say the actuals are above the approximations. All right. Making you do a little bit more work because I'm approximating square root values. And these are the things we can actually check. But it says like use points on a function that you know. What are some points on the square root function that I know? Well, I know that f of 4 equals 2. I know that f of 9 equals 3, right? Don't we know that? Like the square root of 4 is 2, square root of 9 is 3. Cool. So here's the key to these questions. It's like, what is root 5? Well, that is the y value that I'm trying to approximate when x is 5. This is the y on the curve that I have no idea what is equal to. Many students have many mistakes with this problem because I'm giving you like the y value and you decide to use it. But no. We have this 0.42. We're ready to use a tangent line that will mimic this curve around the 0.42. The slope of the tangent needs to be known. We need the slope at 4. Well, that's easy. Plug in 4, we get 1/4. Now, I will use this equation for both of these. I'll say f of 5 will be approximately, I'm going to move the 2 over and just do my work. And say this is y equals 1/4 x minus 4 plus 2. And I'm going to say f of 5 is approximately y of 5. Which means plug in 5 for x. That's 2 1/4. That's 2.25. I think the square root of 5 is approximately 2.25. Now let's do the same for 3.9. So f of 3.9 is approximately y of 3.9, which means I will plug in 3.9 for x here, and I'll get 1/4 times negative 0.1 plus 2. So if we want to change it into a decimal, that's great. If we want to change this to a tenth, that's great as well. It's up to you. Probably we could change it into negative 1/40 plus 2, which is 80/40, and get 79/40. This is the y on the line. Which is approximating this y root 3.9. So I think root 5 is approximately 2.25. I think root 3.9 is approximately 79/40. Which one is going to be more accurate? I know for a fact that this has got to be closer than that. Why? Because 3.9 is closer to 4 than 5 is to 4. So it's like the closer you are to the shared point, the less far away the curve can be from your line. Let's see how we did. We got the square roots. Of 5, 2.23, so we were accurate to the first decimal place, close to the second. Square roots of 3.9, which I think is close to 79/20. Wait, what did I say? 79/40. Bam, 1.975, 1.9748. You know, it's like really powerful. Like it's like crazy how close we are using such a simple method, such a simple thing. Okay. Now we have the 0.93, which is close to 9.25 and close to 10. And I know the slope at 9 using the slope equation is 1 over 2 root 9, which is 1/6. Okay, so we have the equation y minus 3 equals 1/6 x minus 9. And I will use that to approximate f of 9.25. Whose y value is root 9.25, but I'm going to use y of 9.25. I'm going to plug in 9.25 for x, and I'll get 1/6 times 0.25 plus 3. So that's 1/4 of a 6, which is 1/24. 3 is 72/24. So I think it's 73/24. Okay, I think this is approximately 73/24. And then I will do the same thing at 10. Instead of approximating the y value on the curve, I will find the y value on the line. Cool. And I get 19/6. I know that this is going to be probably more accurate. I mean, not probably, definitely more accurate because it's closer to the point that I know. It's really cool to see how accurate we are. The square root of 9.25 is 3.041, and 73/24 is 3.0416. Like this, that's so cool. Honestly, it's so cool how close we are. And it was so easy to do something that seemingly is just really, really complex to be that accurate. We know it's close to 3, but easy to be very accurate. And then the square root of 10, I think, is approximately 19/6. And look at that. We're almost as accurate, but not quite. All right, so closer to the known point, more accurate. Well, what's the second derivative? We knew the first derivative was 1/2 x to the negative 1/2. I'm just going to keep it like that. And the second derivative is negative 1/4 x to the negative 3/2, which is negative 1 over 4x to 3/2. If we are looking at x is bigger than 0, my second derivative is negative. That means f prime is decreasing. That means f is concave down. If we have a concave down function and we're using tangent lines and y's on tangent lines, we know that our values are over the actual. They ask me what would be an actual value. It wouldn't be my approximation. It'd be something under my approximation. Cool. You gotta start with a point that you know. I don't know why I have dots. Everyone is 3. Cool. Imagine trying to do 1.1 cubed plus 1.1 squared plus 1.1. Wouldn't want to do that. So instead, we'll use a tangent line. First, we need the slope. And we got y minus 3 equals the slope at 1, not at 1.1, because that's what we're trying to approximate. We're going to use an easy point. Use the easy point, and we will use that easy point to approximate a hard point. So we don't want the slope at 1.1. We just want the slope at 1. We get 6. And I will say this mimics f of x around the point 1,3. So that means if I want to approximate this y value on the curve, I will instead use my y value on my line. Sometimes it's nice to have like f being the curve and y being the line. By plugging 1.1 now into my lines equation, solved for y by adding this 3 onto the other side. So I got 6 times 1.1 minus 1 plus 3 0.6 plus 3, 3.6. 1.1 cubed plus 1.1 squared plus 1.1. It's just like, it's really cool. 3.6 right there. All right, this one's trickier because I don't give you usually the information that you would be given. So like, here's a typical test question. Given f of x equals the cubed root of x, approximate f of 9 using f of 8 that equals 2. Approximate using a tangent line. If you take a college calculus class, you'd be responsible for like making sure you know what you're talking about, know where you're looking, and so it makes sense. But on the AB exam, they usually spell it out. Okay, so we got the 0.82. So we got y minus 2 equals x minus 8. I need to find the slope. How do I find the slope? I need the slope equation. I need the derivative. Plug in x's, get m's equation. The 1/3 comes down. Don't forget to subtract 3/3 to get negative 2/3. So f prime of x is 1/3x to the 2/3. I need to find f prime when x is 8. I get 1/3 times 8 to the 2/3. You better know how to take 8 to the 2/3. I always take 8 to the 1/3 and square it. So that's 2. 2 squared is 4. 4 times 3 is 12. Okay, so this will mimic the cubed root function around the point 82. I want to approximate the cubed root of 9, which is f of 9. This y value, the cubed root of 9, the y value on the curve will be approximately the y value on the line with 9 plugged in. X equals 9. And if you guys are just copying it down, you're going to mess up on something like that because you're going to plug in cubed root 9 somewhere. But you don't want to. This is 24/12ths. We get 25/12ths. You got to use the x values to approximate the y values. And let's just see how we did. The cubed root of 9, I'm just going to do 9 to the 1/3, is 2.08, and 25/12ths is 2.083. It's unbelievable. It's unbelievable. Cool. You have this question in your notes, making sure you understand it. If you draw a secant line between 1 and 3, which you want to try to do effectively, there's your secant line. We'll call that S. Then you're going to draw a tangent line at x equals 2. I'm just so bad at like nailing these tangent lines. You get my drift. And then you got the function f of x, which is the black line. What's f of 2.1, s of 2.1, and t of 2.1? How would you compare them? Well, like, look. The s value is the one on the bottom. The f value is the one in the middle, and the t value is the one on the top. There you go. Just order them. Same thing here. What about here? Here's the f value. Here's the s value. Here's the t value. The t value now is the one on the bottom. The f value, if you think about it, will always be the one in the middle, unless something crazy is going on, which I can't even think of. And then here, the s value. What's the difference between the two? The concavity, honestly. The concavity and nothing more than that. Nope. Okay, just making sure you know I could be asking this question. What could be the value of f of 2? Okay, this one's a little tricky, but I'll show you how like it kind of works out. You actually don't need this. Oh, okay. I'm just kind of telling you like, yo, pi over 2 is close to 1.57. Imagine me telling you, hey guys, what is 3 cosine of 1.5 minus 1? Be like, I have no idea. But I actually would say it's close to negative 1y. Because let's plug in pi over 2. Pi over 2, cosine of pi over 2 is 0. So I get negative 1. Cool. Let's use a tangent line. Y plus 1 equals sub mx minus pi over 2. Okay, let's find the slope. I need the tangent slope equation. I got negative 3 sine x. The tangent slope equation at pi over 2 is negative 3. I'm going to put negative 3 right here. I am telling you this mimics this around here. So f of 1.5, which I'm trying to approximate here, that y value, I have no idea what that y value, that's on the curve, will be approximately the same as y at 1.5. Now the problem is, like, I don't want to plug in 1.5 here, but watch what I can do after I plug it in. I can distribute the negative 3. Now negative, or I could actually turn it into 3 halves. Watch. Why do I do that? Because it's negative 3 times 3 minus pi over 2, minus 1, which is negative 9 plus 3 pi over 2 minus 1. And I'm just going to leave that value like that, Just leave it like that. And let's see. Whatever that value is, I don't know, but 3 times the cosine of 1.5 minus 1 is that value. And I'm going to do, in a fraction, negative 9 plus 3 pi over 2 minus 1. Awesome. Now, here comes the next question. This is the question that I have the most fun with. What could be the value? Here, same thing. What could be the value of f of 3? This is different from what is the approximation using a line of f of 3. Okay? You are given a point and a slope on f. If you used a tangent line approximation, you have your point, you have your slope. If you wanted to approximate f of 2, you get 2 times 2 minus 1 plus 5. You get 5, you get 7. Cool. So f of 2 must be 7. F of 2 can't be 7. You're told that your curve, and this is the y on my curve, is second derivative positive. Remember, if your second derivative was positive, your first derivatives are increasing, which means your original function is concave up. If you are curving upward, your y's on your line will be below the y on the curve. This 7 is below the actual value. So f of 2, could it be 6? No, because 7 is below the actual value. The actual value could be 8. But it can't be 7 and it can't be 6. Got it? I hope we understood that from class. I think you did. I did a better job teaching it. Here, y plus 3 equals 4x plus 2. We have a concave down graph, which means my y on my line will be above my y on my curve. If I'm approximating f of negative 3, which is the y on the curve, my y in my curve will be below the y on my line. The y on my line is -4 minus 3, which is -7. The y on my line is -7. Since my y on my curve is below that, and since we're in the y values, we'll talk about -8. So if my y on my line is -7, the y on my curve could be anything below -7. This can't be right. This -6 is above it. We already know this is an over approximation. We already know this is above the actual. Again, this is what we're doing with the line. This is what we're trying to find on the curve. This can't be it. It's got to be that. Locations of zeros are when y equals 0. So log x plus x cubed has 1, 0. Use the tangent line at x equals 1. So let's find f of 1. Well, that's 1. Let's find the slope. I need the slope of this, and the slope at 1 is 4. So I got y minus 1 equals 4, x minus 1. And I'm going to say that this will mimic that around x equals 1. I mean, 4 is not really close to 0, but if I said this mimics it close, I could say if y is 0, what is x? It's not going to be more accurate. It's not preferred. I add 4, divide by 3, I get 3/4. But I'll show you visually what we just did, just so it makes sense to you, hopefully. We got y equals log x plus x cubed. And I know at the point 1, 1, we'll have the tangent line y minus 1 equals 4 x minus 1. And like, yeah, you can kind of see we're going to do okay. So what we are doing is finding the x coordinate where your line crosses, which we found was at 0.75. That is very close to the x coordinate where the curve crosses the x-axis, which is at 0.7 something, you know? So it's like we're pretty accurate using the same idea, okay? And that's the end of Unit 4. Unit 5, last unit of the first semester, coming up. Thanksgiving break in between. There's going to be 5 questions from each lesson on your test. So 2 of the 4 are easier. You need to spend extra time on the harder 2 of the 4. All right? Later.